So while I may have butchered my hair this weekend, I still have some math left within me. And I want you to join me this week to complete your training for the AP exam. So happy May the 4th, gals and guys. I hope everyone had a good weekend. And today I do want to continue reviewing, and in all seriousness, I want to look at series today. These are the only topics that you're responsible for being able to apply on your AP exam. Taylor polynomials, you have to be able to construct them. And I really, however, while you have to know that, I really do want to focus my attention today on these topics because these here deal with the convergence of series. So that's your geometric series, your P series, harmonic series, alternating harmonic series, and then the two specific tests of alternating series test and absolute ratio test. And when you are presented with a question to determine the convergence of a given series, the better that you can identify that something's geometric or something's a P series or you have your alternating harmonic series, the easier it will be able to come up with an answer. Because if you have one of these, right, I always say you're going to thank your lucky stars. You can quickly identify what they are and say converges, diverges. If your series is not one of these, then you're going to have to, fall on one of these tests. The absolute ratio test, you want to, if you have factorials in your problem, then okay, you want to definitely use the absolute ratio test. Or if you have exponential expressions in there as well, absolute ratio test typically works. And an alternating series, an easy way to recognize an alternating series is this in your general terms. So if you see this and you don't see factorials or an exponential, an alternating series test is perhaps the best way to go. So with that being said, let's take a look at some of these types of questions. Okay, in this question here in BC2, we have a piecewise function for the function f of t, and we're told that it's given above where k is a constant and w prime is a derivative of the function w. I really don't think we need this for this particular problem. Part D, let d of n equal f of n. For which values of k will this particular series with general term d sub n converge? Give a reason for your answer. Now, to start this off, d sub n, I'm going to first identify what that is, and we can do that because, well, that's equal to f of n, right? So I'm just going to start off writing this out. And now f of n, again, was the piecewise defined function that we have up above. But since we are starting off at n equals to 6 here for this series, that means we're really going to be focusing on this piece of our piecewise function. And, okay, there's a function in terms of t. So I'm going to, here, because we're dealing with a series whose general terms have the variable n in it, I'm going to substitute n in for t in this general term and write this out here. So it'll be negative 2 over n raised to the 3 minus 4k. And when I look at this, especially because k is a variable and I have n raised to this here in the denominator, I recognize this as being something close to a p series. Now this negative 2, I'm just going to pull that out in front of my sigma notation because that is just a constant and we are allowed to do that within a series. And when we do that, we now hopefully really see that we are indeed dealing with a p series, right? This here is just a p series, and we know that this converges when p, which in this problem is this 3 minus 4k, is greater than 1. And so because of that inequality, oops, right, I'm going to work with this inequality to solve for k. And so doing that, we could perhaps, actually I want to avoid having to divide. Actually, I'll do it. We'll have negative 4k is greater than, it'll be negative 2. And to solve for k, we divide both sides by negative 4, and we'll get essentially 1/2 simplified. But be careful, because we did divide by a negative, right? You have to flip that inequality anytime you divide or multiply by a negative in an inequality. And so this would be our solution to when this series will converge, and all this work here supports our answer. Okay, so for our next problem is BC3. We have here, let f of x equal this negative 2 over square root of x, and let capital A equal this series where a sub n equals f of n. Part A, we want to determine whether this given series converges or diverges and explain our reasoning. As in the last problem, because of what we have here, and a sub n is in this part of the general term of our series, I'm going to perhaps just first plug that in to sort of get a sense of things, and then kind of go from there, see what we perhaps have. So that's not a great sigma, but it'll do. So we have negative 1 to the n minus 1 times a sub n, where a sub n is equal to f of n. So I'm going to do that first. And okay, to further simplify things down, all right, negative 1 to the n minus 1, f of n, well, f of n, well, that's associated with this f of x. Just instead of having n, there's x here. And this f of x is equal to negative 2 over square root of x. So I'm going to substitute in for f of n, negative 2 over square root of n. So I'll do that right here. Now, because I do see the square root of n in the denominator again, you may be thinking, well, this might be another p series. But I claim that this negative 1 to the n minus 1 is really going to put the kibosh on the ability for this to be a p series, because a p series really should be positive always, and this is going to just cause an alternation. This is not a p series. At the same time, it's not a geometric series, but, well, I want to get rid of this negative 2. That's annoying me right now. I don't like this negative along with this negative 1 to the n minus 1. So as in the last problem, I'm going to pull that constant out in front of my sigma. So we'll have here now, as a general term, negative 1 to the n minus 1 over just the square root of n. And I said before that this is not geometric. If you don't recognize it right away, you could perhaps start listing out some of the first few terms of the series to verify that. The first term with n equals to 1, I claim would just be 1 over square root of 1. Because of the alternation of signs, the next term would be a negative, and it would be negative 1 over square root of 2. And the next term would be positive 1 over square root of 3. And this is going to continue going on. And actually, that should have been a minus sign. That continues on. And especially with 3 terms, you should then know that, hey, this is not geometric. So it's not a p series. It's not geometric. I got to do one of my tests. I don't see any factorials. I don't see anything raised to the nth power here. I'm left with the alternating series, and I see this, so, yep, this is an alternating series, right? So I'm going to go this route of trying to determine whether the series converges or not. So it's an alternating series. Now my b sub n in this series here, I strip out the negative 1 to the n minus 1, and we're left with just this 1 over the square root of n. And I know that as n increases, that this denominator, even though we're taking the square root of it, I know that's going to get larger, which makes this whole fraction get smaller. And so I know that this is decreasing. And I don't need to do any other work than just state that it's decreasing. And then the last thing that we would do is examine the limit of our general term as n raises off to infinity. And I hope that you would agree that, as n goes off to infinity, this is going to approach 0. And because of all this here, we know that our series converges. And again, this should be all the justification necessary to justify why we know that particular series converges. Okay, so let's look at the next problem. We're still on BC3, so we have the same setup. F of x is this expression, and a sub n is this f of n. Part C, we want to consider this particular series with general term h sub n, where h sub n is equal to this concocted and convoluted expression 2 raised to the f of n divided by f prime of n. We want to find whether this series, or find this series, or show that it diverges. Now, by the nature of how I thought that this was going to say find whether this converges or diverges, it didn't say find if it converges. It says find this, which means we actually have to find this value, or show that it diverges, which means there wouldn't be a sum. And because it's basically saying, hey, find the sum of this if it converges, there's only one series that you're responsible for that you would know the sum to, and that's a geometric series. So by that nature alone, I'm going to look to see if this is going to end up being a geometric series, and if that's the case, then I'm going to thank my lucky stars and go about getting my answer. But to start the process off, like I did in the last question, I'm going to take my given series. I'm going to substitute in for h of n this expression here, 2 raised to the f of n divided by f prime of n. And then I'm going to try to substitute in for the f of n divided by f prime of n. But to do that, I'm going to do it off to the side because, well, first, f of n is going to be essentially equal to this here, except instead of x, I'll substitute n in for x. So we have that f of n will equal this negative 2 over the square root of n, which because I'm going to want to derive that, I'm going to rewrite that as negative 2 to the negative 2 times n to the negative 1/2 power, which using the power rule, our derivative of that would become 1 n to the negative 3/2 power, which simplified would be this 1 divided by n to the 3/2 power. And to simplify, I'm going to simplify this ratio down here first and then plug it in over here. So f of n is this negative 2 divided by n to the 1/2 power, and that's all over 1 over n to the 3/2 power, which we can simplify down by taking negative 2 over n to the 1/2 power and multiplying by n to the 3/2 power all over 1, which when this occurs, because of this here, when we perhaps simplify this, we're just going to have, we can do division here, and 3/2 minus 1/2 would be 2/2, or just 1, and I claim that we would just have here negative 2 times n to the first power. And so that's what I'll put in for my series here. And now I'm really starting to feel confident that we have a geometric series here because this is all raised to the nth power. And to make sure that I do things properly, I'm going to simplify this. 2 to the negative 1/2 power is 1/4, right? And I claim that I can split that up as just 1/4 to the n power because remember, rules of exponents, negative 2 to the negative 2n would be the same as, I'm sorry, this is positive 2, would be equivalent to 2 to the negative 2 to the n, right? Because rules of exponents says we just multiply them, and that's why those are equivalent. So now I know I have a geometric series. R is equal to 1/4, right? And I know this converges since, right, our R value is in between negative 1 and 1. And so now, because it does converge, the actual value to our given series, right, we have that formula for the sum of any convergent geometric series, and that's equal to A, which represents the first term of our given series, which in this case, if we plug 1 in for n, that would be 1/4. And that's over 1 minus our common ratio, which was 1/4. And so that would be the value to this convergent geometric series. And again, all this work here would suffice for support to that answer. Okay, so for our last problem, still on the same BC3 question. So f of x is the same expression, a sub n equals f of n. Part D, we want to consider the series with general term k sub n and the series with general term m sub n. where k sub n equals m sub n times a sub n. If the series with general term k sub n converges by the ratio test, where this limit of this ratio equals 2/3, determine whether the series given by epsilon n converges or diverges, explain our reasoning. Well, by the fact that they told us that this one series that we're dealing with converges by the ratio test, we're going to want to most likely apply that ratio test in this problem. But as I did in the other questions, I'm first gonna figure out exactly what our series is that we have here, and then from there set up our ratio test. So m sub n, the only relationship that I know here about m sub n is this equation here. And so by that fact alone, we can write that m sub n is equal to k sub n over a sub n. And so I'll substitute that in right over here. And this is what I'll work with now as my general term to set up my absolute ratio test for this particular series. Right? And so the absolute ratio test, we take the n plus first term to our series, which would be k sub n plus 1 over a sub n plus 1. And we technically divide by the nth term to our given series, but it's quicker to just multiply by the reciprocal to the nth term to our series, which that would be a sub n over k sub n. All right? And with your absolute ratio test, you typically want to try and simplify things down and rearrange to ultimately help you evaluate the limit of this expression. And because I know that this ratio's limit as n approaches infinity is equal to 2/3, that's the rearrangement of this expression that I'm going to do here. I'm going to rewrite this as the ratio of k sub n plus 1 over k sub n times the ratio of a sub n over a sub n plus 1. Now, furthermore, we learned that this year when we have a product within our limit, right, we can split that into the product, that the limit of the product should equal the product of the two limits. So I'm going to write the limit of this particular ratio here times the limit of the ratio of a sub n over a sub n plus 1. And okay, I now know that that is 2/3, and we are left with trying to evaluate this second limit, which is the ratio of a sub n over a sub n plus 1. Well, a sub n, again, is equal to f of n, and f of n is this here. So I'm just going to plug n in for x, and then we'll have here just -2 over the square root of n all over, and then plug n plus 1 in for n. We would have -2 over the square root of n plus 1. Right, and then for this here, that particular ratio, is getting messy. So I'll over here, I'll write -2 over the square root of n divided by -2 over the square root of n plus 1. We can simplify that to be -2 over square root of n times the square root of n plus 1 over -2. And now these -2's are going to cancel, right? And we're going to have just the square root of n plus 1 over the square root of n. But I claim that we can write that as just the square root of n plus 1 over n, just as one whole term. Right? It's another rule of exponents that because these are both the numerator and denominator raised to 1/2 power, we can take each of these radicands and put that quotient there and then take the square root after that. And because of this here, as I'm running out of room, so we can write down here the limit as n approaches infinity of the square root of n plus 1. And now the square root function we know is continuous everywhere on its domain. So I claim that because of that, and we have a rule of limits that says when you do have a composition, you can take a look at the inner function first, see what the value that is. And if the answer to this limit, the outer function is continuous there, then that would be the answer to your limit. And so the limit as n approaches infinity of n plus 1 over n, I hope that you would agree that that would simply just be equal to 1, which square root of 1 is just 1. And so because of all that there, we can go back to our original problem. We have 2/3 then times this limit, which we simplified down to be just equal to 1. And so the whole kit and caboodle here, the final limit answer is 2/3, which is less than 1. So our given series converges by the ratio test. And so all this work here would be enough justification to satisfy why this particular series converges. So that's it. I hope that this particular video helped you with further understanding your knowledge of series and convergence tests. And if you have any questions on this video or the homework problems today, please let me know. And remember, may the fourth be with you always.